Okay, so here's our second video on the examples of the antiderivative rules. So in this one, I'll do a cos rule, a sine rule, a ln rule example, and an exponential rule. Maybe at the end, we'll do a inverse tan rule, but I might save that for another video. So we'll see when we get there. Okay, so here we go. F prime, f prime of x. Let me change this notation to f of x then. We've got a radical here. Of course, that's the exponent of 1/2. So maybe what I'll do is I'll keep this just the way it is, and I'll change this to that first so you can see exactly what I'm going to do. So now when I go to, say, f of x, I can add 1 to the half, which is x to the 3/2, divided by 3/2, and we'll reciprocal that, plus 4 sine 3x divided by 3, as the rule says that you have in your notes. Because again, the derivative of sine is just cos. So for my final answer, I'll reciprocal this, x to the 3/2. I know I'm kind of squishing it in here, plus 4 sine 3x over 3. So you can see I used the power rule and a trig rule there. So that example is more about the trig rule than it is a power rule, because we already know how to do power rule. It's just a little thing about changing the radicals into exponents so that you can actually apply the power rule to it. Okay, so I guess you know what we forgot, or what I forgot, plus a constant. Holy, I don't know if I'll ever get that. Here we go. Here's another situation where I can see already this issue here. Well, we know some identities, and you can always apply identities if you wanted to make something easier. So I would say f prime of x, and I would leave that cos 2x, and I would change the tan into sine of 2x over cos 2x. Now, this is a fairly straightforward one, right? And we'll see some later on where we won't be able to do that. So f prime of x simplifies down to sine of 2x. So now we can say the antiderivative of that is the negative cos 2x over 2. Because again, the derivative of cos is negative sine. This happens to be a positive sine, so it must have been a negative cos when we did that. And plus our constant. So again, just following the rules. Just what's the antiderivative rule of sine kx? It's negative cos kx over k. What do we got here? We got the derivative is 1 over x squared, so that's a 1 over a function. And the key about this function is that my power on my x term is linear. That makes a big difference, and that's what kind of tells me that this is the ln rule. So when I do this, I should change the notation on these guys here as well, that this is going to be a ln example. Because that exponent's a 1, right here, I'll put it as a little 1 here. That's where I'm going to use the ln rule. When we get into things where x squared's involved and higher exponents like this, you got to be careful on that. And usually there's something else going on in that question. But when it's linear, it's pretty straightforward. It's just the ln of the absolute value of the function, and then of course plus your constant in there. And that's as hard as it gets for those ones. Okay. We've got a Euler's number, an exponential function. So the antiderivative of 1, well, that's like x to the 0. So we'll just say that's x to the 1 divided by 1 plus e to the negative 3x, because we know the derivative of e to 3x is e to 3x. Going back, we divide by that a value in front of the x. So if I simplify this, just because my OCD will not let me sleep if I don't, e to the negative 3x over 3. Using your Euler's rule, and I'll squish in because I forgot again, plus a constant, just like so. So as you can see, the rules are pretty much just exactly what they are. You just apply them throughout. Let's look at the first one again. Yeah, we just used power rule. We just used the sine rule, the cos rule. We used the sine rule, used the ln rule, used the exponential rule. Maybe we'll save the inverse tan function for its own page.